Okay, kiddos, here's a little introduction to work and energy. And when we talk about energy, we talk about both potential and kinetic energy. So I think you have heard these terms before. And this is a good example. We have a bicyclist. So the bicyclist is moving, has some kinetic energy, and is pedaling. They're putting energy into, so we could say that the system is the person in the bicycle, and there's energy that has to go into that in order to move them up the hill. Once they are at the top of the hill, we say they have potential energy. And this is, I know we're not supposed to use the word in the definition, but it's because they have the potential to gain kinetic energy as they roll down. So then they start rolling down, and energy is going, well, I'm not going to say it's going out of the system. What happens is the potential energy turns into kinetic energy as they roll down the hill. So their potential energy will decrease and their kinetic energy will increase. These are sometimes the symbols. Work is almost always a W. Energy, sometimes it's E sub P and E sub K. And sometimes you will see something like U sub P or U sub K, and so U is the variable for energy, and then sometimes you'll just see this like potential energy or kinetic energy. So in terms of definitions, we can say potential energy is the ability to do work or turn into kinetic energy. We'll talk about what work is exactly. And then kinetic energy, the definition would be the energy of motion. So this is the classic example, is there's a mountain and then there's a big rock. This looks more like a yoga ball, but whatever. And when the rock is up at the top of the hill, it has potential energy because if it's given a little nudge, it will start rolling down and speed up and speed up and speed up and speed up. So it has the ability to gain or turn into kinetic energy. It will speed up as it rolls down the hill. Once it's moving, it then has kinetic energy. So the taller something is, the more potential energy it has. So this is, let's say this is height. It turns out that the potential energy, I'll write it slightly differently, potential energy is mgh, and we'll talk about these formulas here in a minute. But mass, the more massive something is, the more potential energy it has. The stronger the acceleration due to gravity, the more potential energy something has. And then the higher something is, the more potential energy something has. And then when something starts moving and it picks up speed and picks up speed and picks up speed, it's picking up or gaining kinetic energy. And so I challenge you to think about what variables do you think the kinetic energy depends on. I'll give you a moment. Okay, so hopefully you thought, well, the more massive something is, the more kinetic energy it will have, and the faster something's going, the more kinetic energy it will have. That's good. That's excellent, actually. It turns out that our formula for kinetic energy is 1/2 the mass times the velocity squared. So here are our formulas. Work, so you go to work or you do work. It means you're exerting yourself. But in physics, the formula or the quantity is something similar to what we're used to. Work is equal to force times distance. So if you exert a force through some distance while you're doing work, force times distance. Potential energy, mgh, and kinetic energy, 1/2 mv squared. So each of these things is measured in joules. Joules, and work is also joules. So it turns out that if we take a Newton, turns out that if we take a Newton meter, that is equal to a joule. And let's see, mass, that's kilograms. So kilograms times meter per second squared times meters That's going to be joules as well. And then mass, so kilograms, and then meter per second squared. Each of these things, if you sort of simplify them, turns out to be a joule, so 1 joule of energy, which is related to the calorie in that, what is it, 1 calorie is 4.184 joules. It might be the other way around. We'll look that up. Okay, so let's talk about doing work. So here this person is pulling on this crate, and they're not pulling exactly to the side, but they're going to pull the crate through some distance, and so they would end up over here off the page like so. Alright, so they pull the crate through some distance, and what we're talking about is that the work that she does is force times distance. So let's say she's exerting a force of 200 newtons. Do you see how, because she's not exactly pulling to the side, only part of her force goes to moving this thing to the side. Some of it is actually, she's actually kind of pulling up a little bit, which doesn't do any work on the crate. So there's another stipulation here in this formula, and that is that the force has to be in the direction of the distance it goes. Force has to be in the direction of the distance it goes. So like, let's say this is your physics teacher on a skateboard. I am exerting some force on the skateboard, and I'm just rolling along a nice smooth sidewalk. I'm not doing any work. Yes, I am pushing on the skateboard. Yes, we are moving through some distance, but because they're in completely opposite directions, they're at right angles to one another, I'm not actually doing any work. If I were to, let's say it's not such a smooth surface, and so I actually have to push, and so here I am pushing on my skateboard, and if I exert a force in this direction on the skateboard and the skateboard goes in this direction, then yes, I'm definitely doing work, but in this case not. So it's only, this is where that cosine of the angle comes into play. It's only the component of force that is parallel to the direction of motion. I'll say that once more. It's only the component of force that is parallel to the direction of motion. So we have recently done some practice with SOHCAHTOA, taking forces at angles and breaking them down into horizontal and vertical components. So the work that this person does would actually be the force times the cosine of the angle times the distance. So yes, it's force times distance, but this is 200 times cosine theta. This is the actual component of force that is parallel to the direction of motion, which I'm just guessing here, looks something like maybe 150 newtons. So she could do more work if she would actually pull to the side in that direction. Okay, and then lastly, bow and arrow. So this is just, I like this because it's sort of showing this, we could call this elastic potential energy. So as it is, nothing's happening. What happens is the archer exerts a force on the bow or string through some distance. So the string started here, it ended up here, and this archer pulled, so exerted a force in a distance, did work on the bow. And in doing that work, what that actually translated into is creating this elastic potential energy, because when they let go, the string is going to move to here and the arrow is going to fly out, and the arrow is going to have some kinetic energy. So what happened is they did work, and that sort of translated into potential energy, and that's actually elastic potential energy because it's stored in the sort of bend of the bow. And then when they release that, that is going to then turn into the kinetic energy of the arrow. So these quantities, work, potential energy, kinetic energy, end up being very helpful for us in studying motion because we can, because they transfer or translate back and forth between one another. And in many instances, it ends up being easier dealing with these quantities than talking about force and velocity and acceleration. One last example. I don't think we're over the 15 minutes yet. So I have one more example. Never mind. All right, so the demonstration that I like to do is this, where I ask for a volunteer, and they stand in front of the class, and I give them a book to hold. And they hold the book. And then I give them another book to hold. And then another book to hold. And then another book to hold. And then another book to hold. And so and then everyone starts laughing, except this poor person. And then another book to and then another book to hold. So anyway, this person ends up really exerting themselves, and so here they are, they're sweating. Oh, it looks like they're crying. Both, they're crying and they're sweating. Here's a big drop of sweat. And but the reality is they're not doing any work. So yes, they are exerting some force in order to keep those books from falling. But you see how the books aren't actually moving through any distance. So the person isn't actually doing any work. If we look at a table, a dumb table that doesn't take any energy, you don't have to put gasoline in it, you don't have to plug it into the wall. The table can do the exact same thing forever without sweating. Okay? It can hold those books steady. Just like this person's doing, but this person, they feel like they're doing work, but in the physics definition, they're not actually doing work because they're not moving the books through some distance. Now, if they were then to lift the books up, so they lift the books up and all of a sudden the books are like this, then all of a sudden they've done some work because they're exerting a force in that direction and they're moving the books from here to here. So they would then have done some work, and the table cannot do that. In order for the table to lift the books up, it has to be some kind of machine, that has to have some kind of engine, that has to be plugged into the wall. And it would take energy in order to do that work.